All right. So today what we're going to do is we're going to talk about our acids and bases. And so this is just to give a little bit of an introduction. You're going to go more over this when you get into Chem 121, but I just want to make sure that we feel familiar with this. So remember that we talked about making solutions. And when we made solutions, we classify things either as electrolytes or non-electrolytes. So electrolytes are when something dissolves inside the solvent. So when the solute dissolves inside the solvent, and then it produces ions. And those ions conduct electrical impulses. And that's why it's so important for your body, is because your nerve endings use those electrical impulses to send signal. So we need those ions in order to help transport those electrons inside your body. Right? Now, acids and bases, they are a special subset of these electrolytes. And so what's special about them is they're going to conduct electricity by making ions, but they're going to make specific ions, or they're going to impact specific ions inside of that solution. And so that's what we're going to be looking at. So remember that when we talk about electrolytes, we talk about them in terms of strong or weak. And strong electrolytes are ones that make a lot of ions. They basically completely disassociate. So this is something like sodium chloride. When we put sodium chloride into our solution, it doesn't stay as a molecule or as a, instead it separates into a cation and an anion. Now, if they only partially disassociate, we can call that a weak electrolyte. And so sometimes why this happens is that their intermolecular forces that hold that molecule together might be strong enough that they are still attracted to each other as a molecule, but some of them can be attracted to the solvent. And so we get this partial dissociation, where some of them will break into ions, but some of them will remain together. HF is a very common example for a weak electrolyte. So what we're looking for, if we're trying to classify things as strong, weak, or non-electrolytes, is we're looking for what they do inside of that solution. How do they break apart? So if they completely break apart, so we only have ions left over, then that would make it a strong electrolyte. If we have a mixture of some ions, but also some of them all together, then that would be a weak electrolyte. And if we have no ions inside, then this one would be a non-electrolyte. Now, the reason why we wanted to review that is because our acids and bases are going to go through a same type of classification. So the first and simplest definition of an acid is our original definition, which is our Arrhenius definition of an acid. And how it was defined is it's an electrolyte that contains hydrogen atoms. And so when we dissolve it, it's going to produce this H plus ion inside of that water. Right? So HCl is an example of that. When we put HCl in, HCl breaks into an H plus ion and the chlorine anion. And so that's our original definition of an acid, is that we need to have a hydrogen inside that molecule. And when it disassociates, then it's going to be that H plus and the anion. Now, just like our strong electrolytes and our weak electrolytes, strong acids produce a large number of H3O plus ions when they're placed in that water based on their amount, whereas weak ones only partially disassociate, so they only make some of those H plus ions. And so you can kind of see HCl is considered to be a strong acid because it almost completely breaks apart. One molecule of HCl makes one molecule of H plus, whereas HF, 1 mole of it only makes 0.03 moles of that H plus. So a lot of it stays together as a molecule and only a little bit of it disassociates. Now, the reason why we sometimes use this H3O plus instead of this H plus is because of something called the hydronium ion. Now, it's okay to imagine it as being this H plus inside of solution. Sometimes that's a little bit easier to work with when you're balancing equations. But the truth of the matter is that if you were to think about it, an H plus ion, well, hydrogen is 1 electron and 1 proton. And so if we remove that electron because we're H plus, then we're really just 1 proton. And so an H plus ion is a proton. Now, this means that they're really reactive because everyone could use a proton, right? So it's a lot of charge. It's got no shielding of electrons in there. And so when it's moving around in water, what we find out is that it readily reacts with water molecules. And so instead of being H plus, it's kind of bopping around in there as this hydronium ion, H3O plus. And so this is a little bit more realistic to how you would really find this in solution, because that H plus is just so reactive that it wouldn't bop around in solution by itself very long. So it's going to collide with a solvent molecule, the H2O, and become that H3O plus. So it's really unlikely that you get much H plus just moving around in there. A lot of times we get this H3O. Now, what I would say about this is that for our class, it's okay if you want to use that H plus, but you do just want to know that that H plus kind of is standing in for that H3O plus. Those things are going back and forth between them. Though, as you're moving forward, you do want to transition to start thinking of it as being that hydronium, right? That H3O plus. And so for our acids, our strong acids produce a lot of this hydronium, which is our H plus. Our weak acids produce some. Right? Now we can also classify acids as something called monoprotic or diprotic or triprotic. So monoprotic means that you make one proton for your acid. Diprotic means you make two protons. And so it's all about, when you put this into solution, if you put one molecule of it, how many you would make. So something like HCl is monoprotic because there's one of those hydrogens inside, so it only can make one H plus and one Cl minus. Whereas something like carbonic acid, it can make a total of two H plus when it dissociates because it's got two hydrogens attached to it. And phosphoric acid, it's a triprotic acid because it can make three of them. Now, just because you can release more protons doesn't mean that you are a stronger acid. Strength has to be about your dissociation percent. But it does mean that for your 1 mole of your molecule, you could produce more hydronium ions than a monoprotic one. So the ability to release more than one proton doesn't equal high strength. High strength is all about whether you dissociate or not. So HI and H2SO4, both of those are considered strong acids. They both completely dissociate. But HF and phosphoric acid are both considered weak acids. So even though there's 3 times, or even though there's more, so we won't talk about 3 times, even though there's more hydronium that's produced from that phosphoric acid compared to that of HI, it's not considered to be a strong acid or a stronger acid than HI because HI completely dissociates, whereas phosphoric acid only partially dissociates. Now, there's not really a great way to get all of your acids. So, sorry, let me rephrase that. For acids, one of the things that you want to consider is you want to just start to memorize some of these acids as you come across them. A good thing to notice is that a lot of our acids, what you're looking for is they're going to start with that hydrogen. They're normally connected to a polyatomic ion on the other side, or they're attached to a non-metal electronegative. Right? And so this is one way that you can start to identify your acids, because acids generally have that hydrogen and that large change in their electronegativities. So them being partnered with a polyatomic ion, kind of a good sign. Now, to tell the difference between strong acids and weak acids is not really a great way except to memorize them. Basically, for our strong acids, there's 3 of them. We have HCl, HBr, HI that you want to know. Then we also have nitric acid, perchloric acid, and then sulfuric acid. And so those are our general strong acids, or very common strong acids. If it's not on that list, then generally speaking, you consider it to be a weak acid. Now, there is one more acid that is sometimes considered to be a strong acid, and it's called chloric acid. And so chloric acid is HClO3. So similar to perchloric acid, it is chloric acid. And so sometimes this one can also be considered strong. It's right there on that cutoff line. Okay. All right. So the reason why we care about acids is we've done a lot of these in our class, and you'll continue to see them. They're called acid-base neutralizations. And so it's the idea that when you have an acid, you can react it with this hydroxide ion. And that's going to produce water. And so it's called neutralization because water is considered to be our neutral compound. And so we're kind of getting rid of an acid, getting rid of a base, and producing something that's neutral. Now, when that happens, we'll always make water as an option, and then we're going to have some leftover ions. And so we can sometimes make that as a precipitate. And then other times what we're going to do is we're going to create a salt. So we have a balance there. And so you do want to know, neutralization is one of those key words. It's giving you an idea about what kind of reaction could be going on. And so you really want to be thinking acid and base. Now, sometimes people don't use those words correctly. You can talk about neutralizations in terms of other things, but you do want to think about that. If it does talk about neutralization, then you want to be considering, what do they mean acid and base? Second part. Let's go ahead and look at this barium hydroxide and how many moles of it would be required to neutralize 0.5 moles of HCl. So the first thing that you have to do is you have to draw out your equation anytime that we're comparing one to another. So this is going to be a neutralization. We have an acid and our base, and so we should make our water. That would give us chlorine extra. Would also give us barium left over. Now, our barium here, you can kind of think of this as being Ba2 plus, and our hydroxide. Now, we would make two hydroxides, so we should use two HCl's in order to balance this out. And so then now we're just to a simple stoichiometry problem. So that becomes 0.5 moles HCl, and 1 mole of HCl is 1 mole H plus. Well, sorry, make that a little bit. 2 moles of HCl is 1 mole of barium hydroxide, since we've already balanced it, and so we can get it 0.25 moles. That's how we can get it to be. All right. So the problem that we kind of run in with bases is that bases were originally defined as Arrhenius as having the hydroxide ion in them. So things like sodium hydroxide, barium hydroxide, lithium hydroxide. So they were all these things that had these hydroxides attached. However, then along came ammonia. Now, ammonia is NH3, but when we put ammonia into a solution, it does a lot of the things that our bases do. So it turns litmus blue, which is a type of compound that has been used to identify acids from bases. But the other interesting part is that when we react it with HCl, it seems to do the same type of chemical reaction. What that means is that when we add in ammonia with our HCl, those protons, that hydronium ion, starts to disappear, and we seem to make a neutral salt solution. And so a new definition had to be introduced, and it was introduced by Bronson Lowry. And what they decided to name their base was that instead of containing hydroxide, a base is just any substance that removes hydronium ions. So now our acid and our base concept is just related to this hydronium. So if you produce hydronium when you get dissolved in water, you're an acid. If you remove hydronium when you get dissolved into water, then you're a base. And so this fits our ammonia. Ammonia gets put in, it interacts with the hydronium in order to produce water, and it itself becomes ammonium, the polyatomic ion. So a definition kind of gets updated. So An acid is anything that donates that H plus or produces H3O plus. And a base is anything that accepts that H plus or removes that hydronium ion. So we can kind of keep track of that, what's going on. In this case, our donor is our acid. So HCl acts as the acid because as it goes through, that Cl is that HCl, but it's lost that H plus. This one is our base because it is picking up that H plus. Now, in a solution, how this works is it kind of goes through this intermediate where it's becoming the hydronium ion, but you can also kind of consider it to be both. Even with just our dissolution of our HCl into water, our HCl is still acting like an acid, still giving away that H plus, and our water this time is acting as the base to produce this hydronium. So our concept in acid and base has become a little bit more global in that you're not just limited to hydroxide ions, not just limited to whether you produce hydroxide ions, you can be anything as long as you're removing that proton or that hydronium. So let's try that. NH3 and so ammonia, and phosphorus trihydride. And we're going and we're producing these as our product. Which of them is going to be our acid and which of them is going to be our base. So you want to make sure that you're paying attention to that forward reaction. So look at what is the change between each of them. In this case, it's lost H plus. In this case, it gained H plus. And so our acid should be that ammonia and our base should be the phosphorus trihydride. In the same way that we talk about acids and electrolytes, bases can be the same. We can have a strong base where you have complete dissociation. You can have a weak base where you guys only produce some of those ions. That part is still the same. So we still talk about strength of bases in the same way. And now, when we're defining our solutions, we define them either as being acid or basic or neutral. And the concept is all based on our hydronium and our hydroxide concentration. So if hydronium is greater, if hydronium is greater, then that is going to be an acidic solution. And if the hydroxide is greater, then that's going to be our base solutions. When they are equal to each other, then it's called a neutral solution. Now, why this kind of works relies on the fact that water by itself does something called autodissociation. So water is in this constant flux where we have it acting both as an acid and a base. So when we have two water molecules, they can collide and they can form hydroxide and hydronium, or hydroxide and hydronium can collide and form water. And so these two things are in what we call equilibrium, where they're constantly going forward and they're constantly going back. Equilibrium, which is shown by this sign here, is something that you guys would see in Chem 121. So because we have this flux, what this does is that in pure water, we actually keep a certain ratio of hydronium and hydroxide there at all times. And so this is going to let us set up an amount or a concentration of hydronium or hydroxide that we should find in a neutral solution. And when our concentration is higher than that, then we know that it's going to be an acid if the hydronium is higher than that. If it is less than that, then we know that the hydroxide must be higher and the hydroxide is going to be the base solution. So that's kind of how we fall into those. So our acidic concentration is going to be when this value is greater than 10 to the minus 7 molarity. And our base concentration is when the hydroxide one is greater instead. And this all comes back to that autodissociation, which is called this Kw. And that K is called what we call an equilibrium constant, which is something that we're not going to talk about this semester, but you'll get a lot of that in Chem 121. So what you want to be able to do with it, though, is that we should be able to then use that information to kind of exchange our hydroxide for our hydronium back and forth. So the thing to remember is that both of those concentrations, when we multiply them together, it's going to give us this value 10 to the minus 14. So as long as we get our concentrations in terms of our molarities, we should be able to translate our H3O plus to our hydroxide, or our hydroxide to our H3O plus. So let's try this. For a solution in which H3O plus is 1 times 10 to the minus 5, what would our hydroxide be? Well, we know 10 to the minus 14 is equal to our H3O plus times our hydroxide. So 10 to the minus 14 is equal to 1 times 10 to the minus 5 times our hydroxide. So our hydroxide is equal to 10 to the minus 14, 10 to the minus 5, and so it becomes 10 to the minus 9. So now we're comparing. We have a concentration of our H3O plus is 1 times 10 to the minus 5. And our hydroxide as being 1 times 10 to the minus 9. And so now we're trying to see who is higher, right? And so hydronium is definitely a higher concentration. 10 to the minus 5 is a bigger number than 10 to the minus 9. And so this is going to be an acidic solution. Okay. Now, you might have heard pH as a term that's used to talk about acids and bases. And the term comes from the idea that instead of saying 10 to the minus 5 and 10 to the minus 9, it's kind of a mouthful to say. They wanted to simplify that down. And so they came up with this equation where pH is equal to the negative log of whatever that concentration is. So 1 times 10 to the minus 3, the pH of that becomes the negative log of 1 times 10 to the minus 3. And that negative and then log of 10 to the minus 3 becomes minus 3. So that's how we get a pH of 3. Now, the thing to remember is that the lower your pH is, the greater the concentration. All right? Because 10 to the minus 1 is a pH of 1, and that's bigger than 10 to the minus 2, which is a pH of 2. So the higher your pH is, it's not more hydronium ions, it's actually less hydronium ions. So 7 is what we consider to be neutral, because that's where we have 10 to the minus 7. As that becomes more acidic, our pH drops as this value goes up. pH greater than 7 is our base, because our hydroxide is now increasing, and as our hydroxide increases, then our hydronium goes down. And so if we want to know the concentration of hydronium for a solution with a pH of 12.2, we should be able to find that, which is pH is equal to the negative log of your hydronium. We know that this is 12.2. And so this becomes 10 to the negative 12.2 is equal to our hydronium. And we can see that as being 6 times 10 to the minus 13. And so that's what our pH scale is kind of telling us. So our pH, some of those things, stomach acid, really low pH, right? 1 or 2, right? Lemon juice is a little bit more than that. Coffee is a little bit acidic, so is most rainwater. Rainwater gets acidic as it comes through the atmosphere and runs into different gases. Things like pure water or human blood, that's going to be neutral at 7. A lot of our cleaning supplies are actually basic, things like ammonia, bleach, right? And then your oven cleaner. So you can kind of see where they kind of fall along with that. Now, the reason why we want to talk about this is because we want to be able to do our titrations. And so just remember that our titrations are a common way for us to use a known solution to determine the concentration of an unknown solution. And so in an acid-base titration, the titrant is the thing that we slowly add to, the titrant is what we're trying to determine, and then we're slowly adding a known concentration from a burette. And so the end point is when we've reached the end of our reaction, and that is going to be used to is going to be shown by an indicator, indicated by indicator. But that seems funny, right? And so the indicator, what's going on is it has a chemical change that changes its color at that endpoint. And so that's when our pH has now drastically changed. And because it's drastically changed, then the structure of that chemical has changed. And so we see a color either produce or a color change. Now, equivalence point and endpoint are two different things. Equivalence point is when our acid is equal to our base. And ideally, our equivalence point should line up with our endpoint, but sometimes that can be a little bit hard to line up. And so that's what we're looking for our titrations. So let's try one. 42.5 milliliters of 1.3 KOH are required to neutralize 50.0 milliliters of H2SO4 or sulfuric acid. What is the molarity? And so our first part is we have to do our equation. So we have H2SO4 and KOH. Now, if you're not sure what to do, then make our boxes. We have H plus, we have SO4, we have K plus, we have hydroxide, and we can look at what we should be producing. Now, H plus and OH, that becomes H2O. That becomes K2SO4. And so now we have H2O, which is a liquid, K2SO4. We look at the solubility rules, and that's going to dissolve, and so that's going to be aqueous. We got to balance that, so we should get two of these. And if we have two of those, then we should get two of those. All right, so just like we were doing with our predicting our reactions, right? So now that we have that, now we can start to do the next part. So we are looking for the equivalence point. So we are looking for when our H plus is equal to our hydroxide. So if we have 42.5 milliliters of KOH, we're going to try to get that to our hydroxide. So we know that 1.3 moles of KOH is inside of 1 liter of KOH solution. We know that there's 1 liter in 1,000 milliliters. And we know that 1 mole of hydroxide is 1 mole of KOH. So what this has done is this has removed our milliliters, removed our liters, changed our moles of KOH into our moles of our hydroxide. So 42.5 times 1.3 divided by 1,000 tells us that we have 0.05525 moles of hydroxide. Now, we want to set our moles of our hydroxide equal to the moles of our H plus. So 0.05525 moles of our hydroxide. We know 1 mole of hydroxide is equal to 1 mole of our H plus. And we know that 2 moles of H plus is 1 mole of H2SO4. Right? And we can see that from our original equation. This sets us, so now we have 0.027625 moles of H2SO4. If we think about sig figs, we really should only have 2, so 0.028. but 0.02765 moles of H2SO4. We can divide it by the volume, 50.0 milliliters. And there's 1,000 milliliters inside of 1 liter. And now that's going to give us our moles per liter. And we get something like 0.55 molarity. And so that's kind of how you would do a titration one. So you can set up your equation, you can look for your equivalence points, set those equal to each other. There's a couple other practice problems that you can do, not about acids and bases, but just about some other multi-step problems, kind of like what you guys would be seeing on your final. So that'd be a good one to do. And then we can talk about them next time we meet. Good luck.